So today we are going to specifically look at solutions. We've done liquids, we've done solids, and let's flip on to, let's go through all of these. We've done all of this stuff already. To the page that talks about different types of solutions. There we go. So looking at this little table, I just want you to kind of get out of your head the typical understanding or the typical thought process that solutions are just liquids, right? Because there's all different kinds of solutions. A solution is just a mixture of some certain things. Thanks. Here is air. Air is a solution, even though we might never think that. Air is a mixture of gases in solute and solvent form, making a solution that is a gas. Who remembers what a solvent is and a solute? What's a solute? The thing being dissolved, and the solvent is what's doing the dissolving. Usually they differ by the amount. It's the one that's usually more of, that's the solvent. It's just semantics. I wouldn't lose any sleep over it. And then vodka and antifreeze. I'm so glad the textbooks decides to use alcohol for an example. That's just great. So we're mixing two liquids together. Our solute and solvent are liquids, making a final solution that is a liquid. Brass, we already looked at the other day. What was in brass? Who remembers? Copper, exactly. And that zinc and copper together are solids, making a final solution that is solid. Carbonated water, you all know that. Soda, Coca-Cola, all that stuff is gas bubbled through a liquid, and our final solution is liquid. Seawater and sugar, don't know why they decide to make a mixture of that, because I don't think that happens all the time. You mix your solid salt with your liquid seawater to make a final liquid. Then you can also take a gas, and because of all the sea of electrons, it's possible for some tiny gases to hang out and surround the molecules in metals, again, because of that electron sea, those delocalized electrons. So you can have a solid that looks solid, but there is gas that had been bubbled over it and have made some sort of intermolecular force attraction with the molecules of the solid. So those are some examples. There are different concentrations of solutions that you need to know. This is all review. We're going to fly through this. Y'all remember molarity, moles of solute over liters of solution. Mass weight percent is something they often use in medicine. I don't know if you've ever seen a hospital IV bag. It says 5% saline on the bag. They use percent by mass or percent by weight. And all it is the mass of the solute over the mass of the solution. So this has to be the mass of the solute plus the solvent, and then we have to multiply by 100. Mole fraction, remember we already did this with, gases, remember? Moles over total moles. So just keep in mind that you have to have moles of whatever you're looking for on top over the sum of the moles of, again, solute plus solvent. Now, molality is something you guys covered in Chem 1. It's something I'm not thrilled about getting rid of, but they took it off the AP because they're not going to have you do any colligative property calculations. They're only doing colligative properties theoretically and through trends, and that's what we're going to talk about on Tuesday. So know it exists. You don't need to do anything with it. Okay, so now we're going to practice these super quick. To make our lives fast, I've put the molar masses on the board to the left. So if you have 1 mole of sugar in 125 mils of solution, calculate the concentration. Molarity is moles over liters, so that's 0.125 liters. And so what do we get? This is where I need you all with the calculators. That's why I said to get this. We want 3 sig figs, so it is 8.00 moles per liter. You have 10 molar sugar. Ooh, that's a lot. 10.0 moles per liter. What is the volume you need to have 2 moles? Math is hard. I need 3 sig figs, please. 0.200 what? Liters. All right. Consider separate solutions of sodium hydroxide and KCl made by dissolving 10 grams of each in 250 mils of solution. Calculate the concentration of each with units. So both of these are going to have, so I'll do this is my sodium hydroxide, this is my KCl. They're both going to have 0.250 liters. So what do I need to put on top to get molarity? Moles. So I have 100 grams of NaOH. I'm going to convert it to moles. What do I get? For every, and I have it on the board here, for every 1 mole, I have 40.0 grams. So it's 100 divided by 40 divided by 0.250. What do we get? I want 4 sig figs. 10.00 moles per liter. And then KCl, I have 100 grams, got to convert that to moles. For every 1 mole, I have 74.6 grams. Thank you. 5.362 moles per liter. So are we good with molarity? That should be a piece of cake for you guys at this point. Whoa, come back. Mass percent. Mass percent is the mass over the mass. This is actually the easiest one because you don't have to flip and convert to moles. But if we want mass percent of glucose, we want the actual grams of glucose over what? Total grams. So I'm going to have 5.5 grams divided by 78.2 plus 5.5. And then my grams cancel. What else do I have to do to get a percent, though? Exactly. So to 2 sig figs, what's my percent here? 6.6% glucose by mass. Unfortunately, you kind of have to write, there is no unit for percent by mass. You just have to write percent, and then usually you need some sort of descriptor. Is it percent by volume? Because that actually exists, even though we don't need it in this class. There are some times you can do percent by volume. So you kind of need to know what we're talking about there. Okay? Are we good? Ready for mole fraction? All right. A solution of phosphoric acid was made by dissolving 8 grams in 100 mils of water. Calculate the mole fraction. So for mole fraction, we need moles of both. So we need grams of both to get moles of both. I see I have grams of phosphoric acid, but they don't give me grams of water. They don't give me grams of water. They only give me mils of water, but they say something that's helpful. The density. You cannot just assume water's density is 1. You either have to be given something like this, or if it's at 25 degrees Celsius, you can make that assumption. So just know you have to see some sort of clue on that. So we actually then know that this is not 100 mils. This is also 100 grams. So what's the first thing you guys want to do? Convert both of those to moles. So this is grams H3PO4. For every 1 mole, I have 98.0 grams, molar mass on the board. So what do I get for moles? Give me 0.0816 moles. Let's find moles of water. I have 100 grams. For every 1 mole of water, I have 18.02 grams. Moles. All right, so now what do I do? Exactly. 0.0816 over the total of 5.5 plus 0.0816. My mole fraction is a big X, and I'm looking at H3PO4 is equal to, do I multiply this one by 100? No, leave it as a decimal. Give me 3 sig figs. 1 what? 4? And that is my mole fraction of H3PO4. Again, no percent. Don't literally make it a fraction because that's an unlimited number of sig figs. It needs to be a fraction as a decimal. We good with math? Yes. Because that is what mole fraction is. See this X? Okay. All right, molality. All right, that's easy. Okay, this is going to be probably the most important thing of the day that we're talking about, and that's the dissolving process. First, I'm going to kind of show you, and those of you at home will be bored. You won't really see what I'm doing, those listening at home. But the rest of you are going to look at this. In my left hand, I have NaCl, okay? It's two ions attracted to each other. In my right hand, I have, it's okay, Peter, relax. Maybe I need to move to her desk. A little too jumpy there, Peter. All right, in this hand, I have water, okay? First off, we know from experience that these two mix. I hope you realize that. They're soluble. They're what we say miscible. They will dissolve in each other. So the question I have for you is, what thermodynamic thing is making this even happen? Why isn't, when I put salt in water, why doesn't it just make a big fat layer on top? There's some sort of thermodynamic thing in the universe that's making mixing happen. I know I can see he wants to say it. It starts with an E. Entropy. What is another word for entropy? Disorder. Nature tends to disorder. Right now, we have a very ordered system as is. If I were to put water and salt together and it all stayed separated like this, well, the universe is not like order like that. The universe wants disorder. So that's the driving force behind any dissolving things. I need you to understand that first. Now, some things won't mix, regardless of the push of entropy. So why don't those things mix? Well, there has to be an energy benefit to the system, or it's not going to happen. So let's talk about what has to happen for these two things to dissolve. This thing on the left, the sodium chloride. What's holding these two things together? Electrostatic attraction. This is an ionic bond. So in order for this to mix with something else, I have to break the ionic bond, correct? Do we agree that takes energy? Okay, so I've done this. I've put in my energy here. So hold this. Energy was invested in that. What has to happen to the water molecules for mixing to happen with that? They have to separate as well. So what are we doing? We're overcoming intermolecular forces, which is what? Which intermolecular force in this case? Hydrogen bonding. That takes energy. Okay, so I'm just going to give 2 to you. So that took energy too. So now I put in this energy. So in order for mixing to happen, these two things have to be as attracted to each other as they are to themselves. There has to be a reason they want to get together. Okay? So because those are ions, because that is super, super polar and has these really polar ends, they will, y'all can come together and mix up. You'll have to turn the, yeah. They come together and mix up, and then they have a nice little mixture here. Okay? When this happens, energy is released. Anytime things come together like this, any of these ions or oppositely charged things, energy is released. Anytime we put in energy to separate, or energy is put in to separate these molecules, energy is absorbed. So energy is released. Okay? How much energy is released depends on how attracted they are to each other. But if they're not attracted to each other, and they're more attracted to themselves before even the separation happened, mixing doesn't occur. So let's say I had oil and water. Okay, it takes energy to separate oil, right? I'm separating oil. London dispersion, not a lot. It takes energy to separate my water molecules, right? Is water like, hey, I want to hang out with oil? Why not? It's nonpolar. Water is more attracted to itself. So there is no benefit or significant energy released when the mixing occurs. So in that case, mixing is not going to occur. Does that make sense? Okay. So let's look at this, how they have it on the PowerPoint, because this is another way to look at the math of it, which is interesting. All right, steps in the dissolving process. They take each step, and they give each step its own delta H. So this first step here, let's pretend that's our ionic salt, okay? It takes energy to expand the solute. In other words, it would have to be to break the lattice there of ions, correct? So this delta H is typically what sign? Energy had to go in. That's going to be positive, guys. It has to be. Okay, things don't arbitrarily separate, because then we'd be in trouble in this world. All right, so this could be our water, and in order to mix, we have to overcome the intermolecular forces by putting energy in. So again, delta H2, 1 and 2, would be positive, because those things are separating the solute and the solvent. Now, when these guys come together, if they want to come together because they're attracted to each other, we get a delta H3, which is typically what sign? Negative. Okay, awesome. To get the total heat of the solution, you add those up. Now, this could be positive or negative. When would it be negative? When these guys are like, hey, we like each other, and they will really be attracted to each other and release a whole lot of energy. Okay, you saw this in the hand warmer lab. Remember, you had some that were most of them were exothermic. It was a hand warmer lab, right? But didn't you have a few that were endothermic? Okay, in that case, the energy required to separate them was more than how much was released, because they weren't real jazzed about being near each other. They still could. They still had some attraction, but not as much as they had for where they were before. So this energy ended up being a really small negative value, so the positive sum of these two overcame this negative, making it overall endothermic. Make sense? All right. I think this stuff is kind of cool, but that's just me. All right, so this is just a verbal repeat of what we just covered. Steps 1 and 2, which is the separation of the solute and solvent, requires energy, so it's usually going to be positive. Step 3, them coming together, releases energy. Steps 1 and 2 are always endothermic, and 3, I'm going to say for our class, we're going to say it's exothermic. Otherwise, it's not going to come together. You'd have to force it to come together, and that's totally not an energetic, beneficial push for it to happen. Enthalpy change associated with the formation is the sum of those 3 steps. Delta H of the solution may have a positive or negative sign, like we said, and this dictates whether the final solution, after dissolving, is endo or exothermic. And again, you did this experiment in thermo. Would you have liked to have, and this is something I've thought a lot about, would you have liked to have known this before you did that lab? Because I still would have to teach you delta H first, though. I'm just wondering if it would have been too much at one time. Anyway, I'm batting that around in my head, because this would have made the lab, I think, kind of more meaningful. I don't know. We'll see. I'll think about it. All right, so these graphs were a little confusing to me. If you're really getting confused right now at this point, just kind of shut your brain off, and I'll tell you when to come back. It took me a minute to realize that an up arrow on this graph means you're putting in energy. And a down arrow, energy is coming out. So we know that delta H1 and 2, you're always putting in energy to separate the solute and solvent. So in this case, we're putting in that much, right? When they come together, we're releasing, when they come together, we're releasing a whole bunch. We're releasing a ton. That much is released. So when you add these positives to this negative, this is how much you get, which is going to be positive or negative? Negative. So this is an example of a graph of an exothermic reaction. Okay? In an endothermic situation, we're putting in this much energy, but when those things come together, barely any energy is released because they're like sort of attracted to each other, not so much. So the overall energy, we put in more than we got out, so this would be a positive, making this reaction endothermic. Make sense? I'm showing you all these different graphical ways because at some point you're going to have to come up with a way to explain it. And so now you have a couple ways. You can explain it this way. You can do it in words. You can do it with pictures. Okay? I'm the fan of the pictures just because that's how I see things. So now we're going to explain why oil and water do not mix. It says address how delta H plays a role, but because they're not mixing, I don't want you to sit there and do delta H1 and 2 because they're not going to mix. We know they're not going to mix. Why are they not going to mix? Polarity. There is a polar and a nonpolar molecule. So the first thing I want you to do before you ever answer a question like this is check that out. If it's not going to mix, then I want you to just explain in words why. Water, and this is, I'm just showing it to you now so you'll have a model to follow after later. Water is, once separated, water molecules are more attracted to what? More attracted to themselves than to what? Oil molecules. So mixing doesn't happen. Delta H, heat. No, I don't want to say that. I think this is an S. I'm not even going to address delta H here. This is just not, I'm going to say not energetically favorable. The occasions I want you to use the delta H explanation is when you're explaining why something's endothermic versus exothermic, things that do mix, why they're endo or exothermic. At this point, there's no real reason to talk about the delta H's. It's not happening. Okay? And that's the same question. All right, in general, one factor that favors a process is an increased in probability of the state where the solute and solvent are mixed. What the heck is that saying? That's what that's saying. Entropy. The universe favors disorder. Processes that require large amounts of energy tend not to occur. Example, oil and water. If I had to mix oil and water, I would have to put in way more energy in order to force those suckers together than I would get out. So that's not going to happen. You can remember in your head, tell yourself like dissolves like. Polar dissolves polar, nonpolar dissolves nonpolar. But if you write that on the AP, you will not get credit. I've graded multiple questions with this on there, and they do not accept like dissolves like. If you want to start out in your opening sentence with like dissolves like, and then go on to explain it, that's fine. But you just can't say polar things dissolve polar things. Why? Polar things are going to be just as attracted to polar things as they are to themselves, so there's an energy benefit to them mixing. Okay? Are you guys good in the hood? What time do we get out of here? Oh boy, we got to hurry. Okay. Now let's talk about things that affect solubility. There's 3 factors that can affect the solubility of solutes in solvents. Okay, structure, pressure, and temperature. You actually already know these. These are kind of common sense. Pressure might be kind of weird, a couple things that'll be new to you. But for the most part, I think you already know all this. Structure, you already know things that are polar will not dissolve in nonpolar things and vice versa. Biology has their own terminology for this, hydrophobic and hydrophilic. Hydrophobic things will not dissolve hydrophilic things and vice versa. Y'all know that lipid bilayer? Remember that? Okay, what was the inside of the lipid bilayer? I can't believe I'm bringing up biology. This is your membrane. If that is the cell, okay, what does this have? Think about it. This is all in solution, so which is which? The outside is polar, because if this is all water aqueous, right, that's going to be attracted to the aqueous part. So this is your hydrophilic, water-loving portion of the molecules. And here you've got all the tails of this bilayer, all of them dissolving with each other. They're attracted to each other. Okay? And so that makes this membrane selectively permeable, right? Certain things will go through and not go through. I'll not remember any of that biology. Anyone in Bio 2 right now? Because if you are, I'm going to tell Mr. Martin that you didn't talk. Okay. All right. So that's just structure. Again, we already know all that. How does pressure affect solubility? Pressure changes only affect solubility in gases. We do not see pressure effects on solid and liquid because those molecules are so close together. To make a liquid become a solid would take an inordinate amount of pressure, and it just doesn't happen. Okay? So we only think about it when it comes to gases. So if I'm trying to make a solution, and you can't see it here, but there's two different colors of little balls, so I'm making them different colors. If I have a solution of these gas molecules, and I want to increase the solubility of one of the gases into the other, I can increase the pressure. You see how increasing the pressure will force them to mix because it's forcing them closer together? All right, so if I increase pressure, I increase gas solubility. Increase pressure, increase gas solubility. Got it? All right, and the last one is, so an example of this is your soda. It's sealed to keep the gas soluble in the liquid. What happens when I open it up? Pressure is lost, so now the gas molecules rise because why is the gas getting less dense now? Less pressure, so the molecules are allowed to separate, and them being allowed to separate makes them less dense, and then they can come out of liquid. Got it? All right. Temperature. Temperature does two different things depending upon the solution. If you're dealing with solids dissolving in water, for the most part, except this crazy sodium sulfate, for the most part, as you increase temperature, more and more and more and more stuff can dissolve. Here's sugar. Y'all ever made super sweet iced tea? What do? You heat it up. You get a whole bunch of stuff dissolved in it and then just let it slowly cool. Okay, that's super saturated. So that's because as you heat up the molecules, you're actually aiding in the process of spreading those molecules out, overcoming those intermolecular forces, so more stuff can be dissolved. All right? The opposite, though, is true in gases. If you were, and you can try this at home, it's really kind of fun to watch how crazy that gas comes off and how much gas comes off. If you take some soda and put it in a pot and put it in a pan or something and heat it up, that gas, the bubbles come off. Even when you think the soda's flat, there's so much gas in there and it just starts to bubble off like crazy. So heating up a solution decreases the solubility of gas, which is opposite to solid. Why is that? Again, when you heat them up, what are you doing to the gas molecules? Spreading them out, less dense, leave solution. Okay, so if you ever want to make a Coke go flat, just heat it up. Sometimes you do that when you're sick. I don't know. My mom used to. I can't remember why she'd do that. Like when I was sick or something, or stomach ache, would you get rid of the bubbles for some reason? But I thought the bubbles helped. Yeah, ginger ale or Sprite are my two go-tos when my stomach's sick. But anywho, all right, are we good with that? Whoa, come back. And this is just a synopsis of the solubility. Although solubility of most solids in water increases with temperature, the solubilities of some substance decrease with increasing temperature. And I don't really care for you to know which ones. We're not going to get into that. Predicting temperature dependence of the solubility is very difficult, meaning why is one thing more soluble than something else? It has to do with how the water, the hydrate shell is around the ion, and so we don't even worry about knowing any of that by heart. If they want you to predict a solubility, they're going to give you a chart, and they're going to say, what's the solubility of sodium bromide at 40? You're just going to look it up, and you're going to say that many grams per whatever. You're never going to have to be able to recreate any of those curves. Solubility of gas is typically indirectly proportional to temperature, so decreases with increasing temperature. And that is the end of the day. You have pre-lab over the weekend. Meet in the Bat Cave on Monday. We're going to quiz in there, so you do have a quiz still. We'll quiz in there, and then you'll start working on the lab.